Hi, welcome to AB Video 1.4b Part 2, Limits of Absolute Value Functions. Now, absolute values. This is going to be a little tricky. I know you think of absolute values as easy, but this is going to be a little bit tricky. By definition, an absolute value is a piece function. Because if you think about it, if you have the absolute value of a positive, you're simply going to get that number back. So if x is positive, the absolute value of x is x. Similarly, if x is 0, the absolute value of 0 is 0, and therefore the absolute value of x is x. Kind of looks like a little smiley face with two eyes. However, if you have the absolute value of a negative, if your x inside here is negative, of course your answer is not x because your answer would be negative 3, which you know it's 3. The way to force negative 3 to become positive is to multiply it by negative 1. So this next definition is crucial for what we're about to do in this video. And that is that you understand that the absolute value of x is equal to the piece function x if x is positive or 0, negative x if x is less than 0. Whatever is inside here, if it's the absolute value, and I just picked the word sun, the absolute value of sun equals sun if sun is greater than or equal to 0, equals negative sun if sun is less than 0. So, for example, that's just reiterating what we said up there, and I don't know why that's there. Okay, so for example, down here, okay, the absolute value of x plus 3 equals x plus 3 if x plus 3 is greater than or equal to 0, and negative x plus 3 if x plus 3 is less than 0. So this expression right here is just that expression if that expression is greater than or equal to 0, and it's negative that expression if that expression is less than 0. Now the thing is, you're not going to leave it like that. What you're going to do here is you're going to isolate x in these two inequalities. This becomes if x is greater than or equal to negative 3. This one becomes if x is less than negative 3. Therefore, you could look for the limit as x approaches 3 from the left. Now again, trying to decide which piece to use, approaching 3 from the left means you're approaching negative 3 from the left. You're approaching from the left side of negative 3, which means you'll use the bottom function. You now replace x by negative 3. Negative 3 is 3, minus 3 is 0. The limit as x approaches 3 from the right would be the right side of negative 3, which is where x is greater than negative 3, and therefore you'll use the top piece. So you'll have the limit as x approaches negative 3 from the right of x plus 3. Replace x by negative 3, you get 0. Since both the left-sided limit and the right-sided limit at negative 3 are both 0, the two-sided limit at negative 3 is 0. Then, if we're checking for continuity, we also need to know what is f of negative 3. Well, there's an equals. So we will use the top piece for f of negative 3, and that'll be negative 3 plus 3, which is 0. Turns out that all three pieces of our trilogy are equal to 0, and therefore we can say that our function is indeed continuous at negative 3. Apparently we already went to the next page. Don't know how that happened because I didn't click on anything. Okay, so here's another example. So the absolute value of expression x minus 5 is expression x minus 5 if expression x minus 5 is greater than or equal to 0, and it's negative expression x minus 5 if expression x minus 5 is less than 0. So same exact process. I'm going to go through this one quite quickly. You're going to isolate x in both of these. You'll get x is greater than or equal to 5. Isolate x here. You'll get x is less than 5. When you're looking for the limit as x approaches 5 from the left, you'll use the bottom piece because that's where the x's are less than 5. So you'll use this piece here. Replace x by 5, you'll get 0. For the limit as x approaches 5 from the right, obviously the right of 5 are numbers bigger than 5, so you'll use the top piece, which is x minus 5. You'll also get 0. By looking at these two one-sided limits, you can conclude that the two-sided limit is equal to 0. Okay? Here's another one. I'm not getting into the continuity, I just want to get into the limits at this point. The limit of the expression 3 minus 2x is that expression if that expression is greater than or equal to 0, and it's negative that expression if that expression is less than 0. So you're going to take this, for example, up here and isolate the x. You'll get x is less than or equal to 3/2. And of course, it's negative this expression, which is negative 3 plus 2x, better known as 2x minus 3, if x is greater than 3/2. So again, we'll be looking for the limit as x approaches 3/2 from the left and 3/2 from the right. For 3/2 from the left, we'll use the top piece. Replace x by 3/2, you'll get 0. For the limit as x approaches 3/2 from the right, you'll use the bottom piece, and which is 2x minus 3. Replace x by 3/2, you'll get 0. Therefore, the two-sided limit is 0, and I'm not going to get into the continuity. One thing I want to point out about these questions is it's no surprise, by the way, that with these piece functions, what you have, no surprise that the limit they're asking is the limit as x approaches 3, because 3 is where the two pieces split off. Here's the limit as x approaches 2, no surprise, because that's where the limit splits off. That's where it's possible the limit as x approaches 2 from both sides won't exist, because that's where the two pieces might not meet up. Again, limit as x approaches 1, no surprise. Limit as x approaches 1 from the right, no surprise. Okay? As far as the absolute values are, that's a bit far. Okay, I think they don't have very many with the absolute values, to tell you the truth. Here, there's one here, and there's one here. They don't have very many examples with it. And that's the end of video 1.4b, part 2.